I want to look at the question of if 1200 centimeters squared of material is available to make a box with a square base and an open top, find the largest possible volume of the box. And so this kind of question is an optimization question. And what you're trying to do is find a max or a min. Okay, so this is an application, this is applied max min problem. Some books call this optimization. All right, and there is a process to this. So these can be confusing, but if you follow this process, it'll take out some of the confusion. So number one on the process is we need to get a figure of what we're dealing with here. So in this case, I'm going to have some sort of box, and you don't have to be an art major or anything, just get a decent looking box. All right, so there's my box. And this is an open top. Also, we know that the base, which is also the top, is going to be square. So to denote that, I'm going to put maybe an x here, and then we'll do a y for the height. Okay, now part two of this process is I need to figure out what I know and what I'm trying to maximize or minimize. So in this case, I want to maximize, what does it say? I want to maximize volume. Okay, so I'm going to maximize volume. And the volume of this box is going to be the area of the base, which is x squared, times the height. So I'm going to have x squared y as my volume. That is what I'm trying to find the maximum of. Now what I know, so they give me some sort of restriction, and what I know is this value, 1200 centimeters squared. That's material. So you think, what kind of material do you need to make this box? Well, that relates to surface area. Okay, so what I know is surface area, and we'll call it SA. And how do you calculate the surface area? Well, it's the area of each one of the pieces. So I have 4 sides and a bottom. So the bottom is going to have an area of x squared, and each of the 4 sides is going to have an area of x times y. So I have 4xy plus x squared, and that's got to be a total of 1200. I also know something that just makes sense to us, so much sense that we may not even think to write it down. The x and y have to be positive, right? You couldn't have, we don't want to consider boxes with negative dimensions here. Okay, so what I'm doing now, and this is the same with related rates and other word problems, is I'm taking the information they have, and I realize that it's kind of like when you buy some sort of product and everything's placed in there in a very particular way, and so you have to unwrap it the right way. And that's exactly what we're doing. This process helps you unwrap these problems instead of just dumping it on the floor and then trying to figure out from there. All right, so 3, again, I know I want to maximize the volume here, which is x squared y, but the problem is the only maximization techniques I have are for one variable functions. So can I get a volume of x? Okay, so in step 3, you want to find a function. Okay, in this case, I'm going to say volume of x. I want a volume of x function. And how do you do that? Well, you use what's given to us. So I'm going to use the surface area here, and I'm going to replace y with that surface area equation. Okay, so first of all, let's take that surface area, x squared plus 4xy equals 1200. And I can solve this algebraically for y. So I have 1200 minus x squared, and so y equals 1200 minus x squared over 4x. There's my y. So now I take my volume, which was x squared y, and I replace y with this expression. So that becomes x squared times 1200 minus x squared over 4x. And if you distribute that x squared across, you end up with volume being, let me see, well, I'll just do it. You have 1200x squared minus x to the fourth over 4x. And so you can see here that I have the 1200x squared cancels out with 4x, give me 300x minus 1/4 x cubed. And there is my volume function, and it is a variable of x. Okay, so now I could just ask the question, and this is what I do in part 4. Find, in this case, the max of v of x. So find your maximum. And we know how to find the maximum, don't we? We take the critical points, and then we can use either the first or second derivative point test to see if my critical points give me a min or a max. So here I'm going to find the first derivative of volume, and that's going to be 300 minus 3/4 x squared. And I want to find my critical point, so I set that expression equal to 0. Okay, so that's 300 equals 3/4 x squared, or if I divide both sides by 3/4, that's going to end up with 400 equals x squared, or x equals plus or minus 20. But we remember here, it was so obvious we didn't even think to write it down. X has to be 20. It can't be negative 20. Okay, so there's my critical point. Now, you could test either first or second derivative test. So I'll say first d test. And if you apply the first d test, we find that x is a maximum of this volume function. So x gives me a maximum. All right, so that's exactly what I wanted. And y then would be, well, what is y? Oh yeah, right there. 1200 minus 20 squared over 4 times 20. You'll end up with 800 over 80, or 10. So y is 10, x is 20. Okay, now, for the last stage of this, I think we should always clarify what we're saying with a statement. Okay, so I'll call this part 5, and part 5 is a summary. And the summary is, we'll say, to maximize volume with 1200 centimeter squares surface area, let's let x be 20 centimeters and y 10 centimeters to obtain a volume of, well, how do we find our volume? V is x squared y, right? So that's going to be 20 squared times 10, which is 4,000 centimeters cubed. And there's your max volume with these given conditions. So I hope this makes sense. If you follow this process, it will guide you in the right direction. It will help you unpackage these problems correctly. I'd be glad to help if you have any questions. Please let me know, and thanks for watching.